Every velocity graph hides a physical secret. The area beneath the curve isn't just geometry, it gives you the exact displacement of the object, and under an acceleration graph, the area reveals velocity change. These connections produce the kinematic equations that govern all constant acceleration motion. When the x component of velocity changes linearly with time, the average acceleration equals the instantaneous acceleration at every moment. That defines constant acceleration. Consider a body with initial velocity v0 at time 0. The x component of acceleration over the interval from 0 to t is v of t minus v0, all divided by t. This ratio stays constant for any time interval. Let's rearrange that definition to solve for velocity. We start from acceleration equals the quantity v of t minus v0, all divided by t. First, multiply both sides by t. That cancels the denominator on the right and gives a times t equals v of t minus v0. Next, add v0 to both sides. The result is v of t equals v0 plus a times t. This is the first kinematic equation, and it tells us that velocity is a linear function of time. On a velocity versus time graph, this plots as a straight line. The y-intercept is the initial velocity v0, and the slope of the line is the constant acceleration a. Picture this line on the vt graph. It starts at v0 on the vertical axis and rises with slope a. Positive acceleration tilts the line upward. Negative acceleration tilts it downward. The steeper the line, the larger the magnitude of acceleration. Now examine the acceleration versus time graph. For constant acceleration, it is a horizontal line at height a. The area beneath it from 0 to time t is a rectangle. Its height is a, its width is t, so its area is a times t. Now recall the velocity equation. From v of t equals v0 plus a times t, we can rearrange to get a times t equals v of t minus v0, and that difference is exactly the change in velocity, delta v. So the area under the acceleration time graph equals the change in velocity. Now consider the area under the velocity time line. It starts at v0 and ends at v0 plus at. The shaded region from 0 to t forms a trapezoid. This trapezoid's area equals the displacement delta x. We prove it by splitting the shape into two pieces. Draw a horizontal line at height v0 across the trapezoid. Below it sits a rectangle with height v0 and width t. Its area a1 equals v0 times t. This represents the displacement at constant velocity with no acceleration contribution yet. Above the line sits a right triangle. Its base is t and its height is v of t minus v0, which equals a times t. The area a2 is 1/2 base times height, that is 1/2 times a times t squared. This captures the extra displacement due to acceleration. Now let's add both contributions together. The total trapezoid area is a1 plus a2, which gives v0 times t plus 1/2 at squared. This total area equals the displacement delta x. Writing position as a function of time, we get x of t equals x0 plus v0 times t plus 1/2 at squared. This is the second kinematic equation, and it tells us that displacement equals the area under the velocity versus time graph. There's another useful form for displacement. Under constant acceleration, the average velocity equals v0 plus 1/2 a times t. Multiply this by t to recover delta x. That gives v0 times t plus 1/2 at squared. Notice that the average velocity sits exactly midway between the initial and the final velocities. This midpoint property holds only for constant acceleration, not for general motion. Plot position versus time. The equation x of t equals x0 plus v0 t plus 1/2 at squared traces a parabola starting at x0. Its slope at time 0 equals v0, the initial velocity. The curve bends upward for positive acceleration, downward for negative. These equations handle a wide range of problems. For multi-stage motion, write piecewise functions, one set of equations per phase, matching position and velocity at the boundaries. For multi-object scenarios, write separate position functions and set them equal at the meeting point. A car starts from rest at time 0. It accelerates with unknown constant acceleration along a straight line, covering 100 meters and reaching 20 meters per second. Then it continues at that speed for another 10 seconds. There are 5 quantities to find: the motion equations, the acceleration time, the acceleration magnitude, the piecewise graphs, and the average velocity. Since v0 is 0, the equations simplify to x of t equals 1/2 a times t squared, and v of t equals a times t. Let t1 be the moment when the car stops accelerating. At t1, the position is 100 meters and the velocity is 20 meters per second. To find t1, we eliminate acceleration between the two equations. Substitute a equals v over t into the position equation, giving s equals 1/2 times v times t. Rearranging, t equals 2 times x divided by v. So t1 equals 2 times 100 divided by 20, which is 10 seconds. The acceleration equals velocity divided by time. 20 meters per second divided by 10 seconds gives 2 meters per second squared. Now for the piecewise functions. In phase 1, from 0 to 10 seconds, the acceleration is 2 meters per second squared, the velocity is 2 times t, and the position is t squared. In phase 2, from 10 to 20 seconds, the acceleration is 0, the velocity stays at 20 meters per second, and the position is 100 plus 20 times the quantity t minus 10. On the graphs, the acceleration plot holds at 2, then drops to 0 at 10 seconds. The velocity plot rises linearly to 20, then stays flat. The position plot curves as a parabola up to 100 meters, then rises linearly to 300 meters at 20 seconds. For the average velocity, during the constant speed phase, the car covers 20 times 10 or 200 meters. The total distance is 100 plus 200, which is 300 meters. The total time is 20 seconds. So the average velocity is 300 divided by 20, which is 15 meters per second. Notice the car covered twice the distance at constant speed as it did during acceleration, even though both phases lasted the same time. The higher velocity throughout the second phase explains this. At the instant a traffic light turns green, a car starts from rest with constant acceleration of 3 meters per second squared. At that same moment, a bus passes the car at a constant 16 meters per second. We need to find where along the road the car overtakes the bus. Set the origin at the traffic light with positive x in the direction of travel. Both objects start at position 0 when time equals 0. The car accelerates from rest. Its position is x1 of t equals 1/2 times 3 times t squared, which simplifies to 3/2 t squared. Its velocity is v1 of t equals 3 times t. The bus has 0 acceleration and constant velocity, so its position is x2 of t equals 16 times t. On the position time graph, the bus traces a straight line while the car follows a parabola. Both start at the origin. The bus leads initially, but the parabola eventually crosses the line. At the overtaking time t sub a, the two positions match. Set 3/2 t sub a squared equal to 16 t sub a. Now divide both sides by t sub a, which is valid because the overtaking time is not 0. This gives 3/2 t sub a equals 16. Solving, t sub a equals 2 times 16 divided by 3, which is 32/3, approximately 10.7 seconds. Now substitute back to find the position. x1 at t sub a equals 3/2 times t sub a squared. This evaluates to 2 times 16 squared divided by 3, giving 512/3, approximately 170 meters. So the car overtakes the bus about 170 meters from the traffic light, roughly 11 seconds after the light turns green. At that instant, the car's speed is 3 times 10.7, approximately 32 meters per second, exactly double the bus's speed. 3 results for constant acceleration. Velocity is linear, v of t equals v0 plus at, with the at graph area giving delta v. Displacement is the vt graph area. X of t equals x0 plus v0 t plus 1/2 at squared. Apply these to multi-stage and multi-object problems through piecewise functions and simultaneous equations. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.